So let me welcome you to the first panel, whose title is Proof, What is it and what is it worth? I think for those of us who were lucky enough to see the play last night, I guess there were many people who just raised their hands that they've seen it before. But for those who enjoyed it last night, still fresh in our minds, it's really a wonderful play, brilliantly scripted and brilliantly acted. And it does raise questions about proof and what it's worth. And I guess we have a panel, and I will not introduce them right now, but rather one at a time, briefly, as we get to the panelists to discuss these issues. Let me describe the format of how we're going to proceed, which has been quite confused in the last hour. So maybe the panelists will now also understand what the plan is. So the plan is to have 10 to 15-minute presentations by 3 of the panelists in the first half. So we'll continue for half the period, then have a 5-minute short break, and then continue for the other half of the period, definitely finishing by 4. My job will be to keep them down to their allotted time of at most 15 minutes. I will do that. So the plan is, as I said, 3 of them will make presentations generally related to what they think about and in connection with what the play, I think, raises. And then we will have an open discussion. So that's, I'll do some arithmetic for you, 3, 15, 45 minutes. There's about 10 minutes of discussion of the whole panel, and maybe even 5 minutes with the audience. We want the audience to participate this in as well, and then have a break, and then repeat that for the second half. Usually I ask the audience, well, you agree, is that reasonable? But I think in this situation, we probably better stick by whatever we have now. So it looks like it should be interesting, and I think we will start with Dusa McDuff. She's professor at SUNY at Stony Brook. She's a professor of mathematics. She's one of the world's leading mathematicians. In particular, she recently, or for many years, has worked in symplectic geometry and topology, where she has made outstanding contributions, and she will give us her views on proof and what it's worth. And I think she will need that overhead. So, Professor McDuff.
So what I want to do is to try and give you a little bit of an idea of the kind of mathematics I do and the role of proof in the kind of mathematics I do. So I'm going to try and give you a very simplified introduction to symplectic topology, and then talk a little bit about where proof comes in. Well, so here's just a few words about symplectic structures. That's the best we can do. That's a kind of structure that you put on spaces of even dimensions, dimensions 2, 4, 6, and so on, that underlies the classical equations of motion for systems with conservation of energy. So I study the geometry of these structures. That means their spatial properties. Well, we're going to start with a very simplified model of the solar system. So we've got the sun, which I'm going to consider as not moving, and the Earth moving around the sun in a plane. So that's really, really oversimplified, right? And we want to try and understand, how does the Earth move around the sun? And so first of all, you have to describe it. You have to have some language in order to say where it is and what its velocity is. So you have you have 2 coordinates, x and y, 2 numbers that tell you where the Earth is on the plane. And you have 2 other numbers which tell you how fast it's moving, where the x dot tells you how fast it's moving in the x direction, and y dot tells you how fast it's moving in the y direction. And the position you put with a little dot, and the velocity, you describe it by means of an arrow, which points in the direction it's moving. So you just think it's moving in the direction of that arrow, and as it moves around the sun, the arrow keeps turning. So altogether, in order to describe the state of the Earth, you need 4 numbers. That's why you have to do geometry in higher dimensional spaces, because you need 2 position coordinates and 2 velocity coordinates. So the question everybody's interested in is, how does the Earth move? In other words, if you start off at a point in this state space, so you know where the position and velocity is, and time, it moves through time, you want to know how does it change by time. So that's time evolution, and you describe it by a vector field, which is at each point you have a little arrow telling you where the state would move. If it started, if at time 0 it was at the end of the arrow, it would move in that direction as time evolved. And so the evolution would be described by just lines of motion through the state space, telling you where it is at each time. Now here physics comes in. It tells you that the motion is determined by the energy at each point. At each point there's a number that you can say is the energy, and if you know that number at every point, you know exactly where the Earth is going to move. And what this has to do with symplectic structures is that a symplectic structure is a mathematical gadget that lives on this 4-dimensional space that turns a set of numbers, which is the energy, into the vector field, which tells you the time evolution. So it's a kind of mathematical object that tells you, if you know what the energy is, you know how things move. So here's a little picture of it. Here is state space. Now, to try and draw the function, what I can do is draw the set of points where the function takes a particular value. So the top set of points is where the function is 1, and then you have the set of points where the function is 2, the set of points where the function is 3, and so on. So that describes the energy of the system. And then you have this symplectic structure, which magically gives you this extra knowledge of these little arrows which tell you where things would move. So these little arrows are always tangent to the level sets, the sets where the function is constant. So as the motion goes on, the energy doesn't change. I told you this was describing systems where the energy doesn't change. But another thing doesn't change. The symplectic structure, which is the underlying structure in this space that gives you the arrows, that also doesn't change. If you move along in time evolution, the symplectic structure is carried into itself. So you see, a mathematician starts getting interested at this point and says, well, what kinds of motions are possible of state space that don't change the symplectic structure? That's the kind of question a mathematician would ask. The kind of question a physicist would ask is, okay, I know the energy function for this particular system. Where is it going to move? So the physicist wants to do calculations, wants to get specific knowledge about a particular system. Well, the mathematician is interested in much more general questions. You know, what possible things might happen? Is there anything you can possibly say about motions of this space that preserve the symplectic structure? And one of the things about mathematics is that a lot of the heart of it is in asking the right questions, asking questions where you have a hope of an answer. And for many years, people knew nothing about symplectic structures because there was nothing they could get their hands on. They just didn't know what to ask in a way to get an answer. But in the 80s, various people started having new ideas and had ideas of new questions they could ask where there was a hope of an answer. And one of them is, suppose you take a round ball in your space and move it, preserving the symplectic structure. What shapes does it take? Can it become long and thin? Can it curl around and around in a spiral? And, well, there are some answers, not complete answers, but one is it can't become long and thin. That's a theorem due to Gromov. Now, you see, this question, it's a very conceptual question. And the only way you can possibly get an answer is via reasoning and logic. There's no way that you can do a calculation and answer that question. You really have to develop new ideas, new concepts, and then reason about these concepts. You need some intuition to think what's likely to happen, what possible measurements could you make that would give you some information. You make lots of guesses, and then you say, well, I think this is true, and you make a long chain of reasoning which you hope leads to that conclusion. But that's, the only tools you have to get any information is logic. So here's a little bit about sort of describing mathematics as I see it, that the reasoning is deductive, and you might not think that's very creative, but the creative part is often lying in the asking of questions and also defining new kinds of objects to think about. Because after all, you have to think about something, and the question is, you don't want to think just about a blank, You create something to think about, and that's an interesting process. So for example, mathematicians and physicists had written down and studied the equations of motion long before they thought of the idea of a symplectic structure. So, you know, it was sort of implicitly there, and nobody had crystallized this idea that this is something worth thinking about. And once they crystallized the idea, people started trying to think about it and understand it. Well, that's how I see the process of the kind of mathematics I do. And as I say, I think we only have logic to use as a tool. There's also calculation, and in some fields you can use computer simulations, but really they don't help much in what I do. Physics, on the other hand, is different. Physicists justify their theories by their consistency with experiment rather than by logic. They allow themselves unbelievable, from a mathematical point of view, unbelievable leaps of inaccuracies. But they say it's all justified because they get the right answer, and you know, their theories have the right shape. So they have just other ways of testing the consistency of their theories. And what's very interesting now is that they're coming up with a lot of new ideas and new conjectures which are purely mathematical, and which turn out, whenever they can be checked by mathematicians, they turn out to be basically right. So they have a kind of intuition that they get from studying physics, studying the world, that actually has relevance in mathematics, and I think that's very interesting. So that illustrates that there are many different valid ways of trying to understand the world. And mathematics and physics, even though they have different sources of intuition and different internal consistency, are still on the same track, because when the physicists use their crazy ideas, they come up with perfectly reasonable conjectures. And I think this is not surprising, because our brains and our reasoning powers, all the things we do, mental things, that they've developed and evolved in constant dialogue with the world. And therefore, I think you develop different ways of looking at things, but we're all looking at this, we're all living in the same world. Okay, so that's all I have to say. Thank you for your attention.
Well, thanks. We'll get back to discuss some of those issues, as we said, in the discussion period. So our next speaker is Professor Kit Fine. He's a professor of philosophy at NYU, world-famous philosopher. I know that my colleagues at Princeton have been trying to bring him there. Hope that doesn't embarrass him too much, but he's got sense. He stays here. What can I say? And he is, one of his interests is philosophy of mathematics, and he will talk about comparing proofs in mathematics and in philosophy.
Thank you. It's a great pleasure to be here. My interest in philosophy actually began with mathematics, because when I was at high school, I was worried about the concept of the limit. And this was explained in a book by Bertrand Russell. And I thought, this is great. And then I've pursued an interest both in philosophy and mathematics ever since. I thought it might be helpful if I try to explain what I regard as the way that proof or deductive reasoning is used in these two subjects. Well, at the outset, I think it should be evident to everyone that both philosophers and mathematicians make a great use of deductive reasoning. Proofs consist of long chains, usually long chains of deductive reasoning. And although the reasoning in philosophy isn't always deductive, large parts of it are. However, I think that the role that deductive reasoning plays in these two subjects tends to be very, very different. And it differs both in regard to its function and in regard to its form. So let me make some remarks about this. And when I've done that, I'm actually going to start in a typical philosophical fashion to qualify them. We can use, as a previous speaker emphasized, we can actually use deductive reasoning in mathematics to actually to settle mathematical questions. We have some question about certain kind of structure or what have you. We ask various questions about it, and simply using deductive reasoning on the basis of self-evident mathematical axioms, we can arrive at answers to these questions. Philosophy isn't like that. No one expects to solve by some reasoning analogous to mathematical proofs, the mind-body problem or the problem of free will or what have you. There was a time in the history of philosophy when people did think that. The most notable case is Spinoza's Ethics, which was modeled on Euclid's Elements. But I think there are probably very few philosophers now who think there's any hope of doing for philosophy what Euclid did for geometry. However, deductive reasoning does have a role in philosophy. It doesn't actually provide you with the answers, but it constrains the answers that you might give. So certain possibilities can get ruled out by means of deductive reasoning. So let me just give a very simple example of this, which people often use in introductory philosophy. Here's an argument that there's no free will. Well, if the world is deterministic, if every event has a physical cause, then there's no free will. Because it's not me who did the thing, it's just this physical cause that's responsible for it. But the world is deterministic, therefore there's no free will. Okay. Well, what this argument doesn't actually establish the conclusion, because the premises aren't at all evident. But the argument does present you with a choice. It says either you must be a compatibilist, either you must say that free will is compatible with the world being deterministic, or you must deny that the world is deterministic, or you must give up on free will. And deductive argument shows you that those are your choices. Okay. And indeed, those choices have actually shaped the philosophical debate in this area. Okay. So I just give us a simple example of how deductive reasoning, a simple piece of deductive reasoning, can be of help in thinking about a philosophical matter. Not in providing the answers, but in constraining the answers that you can give. Okay. I also think that there's not only a difference in the function of deductive reasoning, but that there's also a difference in the form that deductive reasoning tends to take in philosophy and mathematics. The reasoning in philosophy is elementary in two distinct respects. First of all, it tends to be short. You don't find long arguments, deductive arguments, in the work of philosophers of the same sort that you find in mathematics. Suppose there was a law passed that no piece of deductive reasoning, any academic research, was to be longer than 1 page. Okay. Most of mathematics would be decimated. And you can't cheat. You can't appeal to some previous conclusion that was established by deductive reasoning. Now, there actually are some very nice mathematical theorems that can be proved in 2 or 3 lines, actually. Some beautiful results of that sort. But most of mathematics would be decimated. Okay. But I think philosophers would be basically unbothered by this. So the reasoning, there tends not to be long chains of deductive reasoning in philosophy. Secondly, the deductive reasoning in mathematics tends to be tricky. It tends to involve what's a construction. You have some sort of novel idea, which you introduce in order to get the conclusion that you want. I mean, a simple example is the proof that the interior angles of a triangle add up to 180 degrees. Yep. So, okay, good. I need the umbrella.
I was going to give it to you at the beginning.
Okay.
But,
so
he didn't want an overhead. He wanted an umbrella.
That's right. So there's the triangle lying on the table, and now I draw. This is the construction. I draw this line parallel to that line there, and then this angle here is going to be the same as that angle there, and just there. And that angle is going to be the same as that one over there. And so you get the proof. The essential. Thank you. The essential. This is how philosophers do their proofs. The essential point here is that there's a construction. You don't just sort of extract the information that's in the situation you're given. You actually have to construct this line. Okay. And all mathematical reasoning of interest involves a construction. It's tricky in that way. Philosophical reasoning tends not to be of this sort. If you looked at that piece of reasoning I gave before about free will, it's of the form if P then Q, P therefore Q. You're just extracting information. There's no clever construction. Strong evidence that this is true is the fact that you do not find mathematicians scouring the philosophical literature for interesting methods of mathematical proof. And I doubt there's probably an instance of this ever happening. So philosophical reasoning tends not to be of mathematical interest. It's deductive reasoning all the same. Okay. So there are these sharp contrasts between deductive reasoning and the two spheres. But I actually think that what I've said isn't, although it's generally true, it's not invariably true. And I think there are some cases when reasoning of mathematical significance is actually of significance in philosophy, can actually be used. Okay. And if there's time, let me just mention two examples of this sort. Okay. One is Gödel's incompleteness theorem. And in a symposium on proof, we have to mention Gödel, who proved things about proof itself. And one way of stating his result is that there's a gap between proof, or at least proof in a formal system, and mathematical truth. That no formal mathematical system can capture exactly the mathematical truths. Now, many philosophers have thought that there's nothing that you might call reconditioned transcendent truth. There's the idea that there's something that could be true, even though incapable of recognizing it to be true, is incoherent. So they've thought that truth must always be accessible in this sense. Okay. Well, Gödel's theorem would appear to show that they are wrong, because it would appear to show that the notion of mathematical truth transcends our ability to prove things. Okay. So that gives the philosopher, the verificationist philosopher, an awkward choice. He must either say, look, the notions of proof or of truth that are used in this theorem don't correspond to the notions that he's using, or he then has to give up his view and say, yes, these two notions must come apart. Let me give a quite different example, not from mathematical logic, but from mathematical economists. The great economist Arrow proved a very famous impossibility result. I'll state it as a result about democracy. It actually arose from welfare economics. So you can think of democracy as providing a procedure for taking you from individual preferences to a group preference. Okay, a voting mechanism is such a procedure. Okay. And what he said is that if this procedure satisfies certain seemingly desirable properties, has some certain seemingly desirable properties, then it can't exist. Okay. So one of the properties, for example, was what he called non-dictatorship, which is roughly the idea that the group shouldn't follow any one individual's preferences, regardless of the preferences of the other members of the group. Okay. So this means, if we're doing democratic theory, that we face an awkward choice. Okay. We must either say that democracy is impossible, or we must say that it's in some ways undesirable, okay, has some undesirable features, because one of these conditions that Arrow says, one of the set of conditions Arrow says can't all be satisfied, will fail to be satisfied, even though it's a desirable condition. Or we must say that somehow the way Arrow has said that this is an implication, or you might think of Arrow as having said this is an implication of democracy, is wrong. There's some mismatch between what he thinks you might think democracy requires and and what's actually required. Okay, so I think that there are cases of this sort in which significant mathematical results have had a significance for philosophy. Now, as far as when I think back, I think that all these cases belong to the recent history of philosophy. I think the trend started at the end of the 19th century, and there have been some notable examples of this in the 20th century. My hope is that this will continue in the 21st century, that there will be considerably more reflection on philosophical concepts. It will be an attempt will be made to discern the mathematical structure, and as a result, the mathematicians can help us work out what are the viable philosophical solutions to the problems which we formulate with the help of those concepts. I might also add that just as physics can be a source of mathematical discovery through the intuitions of the physicists, I actually think the same is true in philosophy, that the philosophers can actually provide insight into how these concepts work, which actually can itself be of help when one comes to doing the mathematics. But since my time is up, I'll just leave that as a tantalizing suggestion. Thank you.
Thanks very much. The next panelist is Michael Rubin. He's professor of computer science at Harvard University, also used to be at the Hebrew University, in math and computer science, I believe. In fact, his contributions have been both in mathematics and in computer science and in randomized algorithms, which he might mention. Professor Rubin.
Thank you very much. I must say, a friend of mine once said, before I start talking, I want to say a few words. So the few words I want to say, I'm really delighted, not on my own behalf, but on behalf of mathematics, to see so many people turning out to hear something about this arcane subject. It brings to mind a cartoon that I've seen many years ago in Punch magazine, now defunct, where they show a speaker on a soapbox at the corner of Hyde Park, the famous corner. And he is standing there and saying, and now the question arises, why are these vital facts so little known throughout the kingdom? And you look at the picture, there is nobody standing in front of him. So I think we should feel quite pleased. Now I want to talk about the connections between computer science and the new field of computer science and the ancient field of mathematics. And in particular, how those connections impact the notion of proof and how ideas from computer science have infused completely new or created completely new points of view for us to consider what a proof is. And I'm going to concentrate on 3 topics out of many possible topics in this domain. And the first one, and Peter has alluded to it, is the introduction of randomization into computation. And I want to mention a particularly surprising fact about that. So we always held mathematical proofs as a sort of a paragon for certainty, a fact that has been proved. Well, even politicians, in fact, they sometimes talk about fuzzy math, but they also want to say that something has been established with mathematical certainty. Now we know that actually in real life this is not so, and there are some theorems whose proof in a sense comprise altogether maybe 10,000 pages, closely argued pages, and I'm referring to the classification of the of the simple groups and finite simple groups, and who knows if there isn't an error lurking somewhere therein, so to speak. Now, it was discovered about 25 years ago that you can establish the correctness, you can establish a mathematical statement by consulting the tosses of a coin. So one example of that, and an enormously important example in technology, is determining whether certain very large numbers are prime or not. And you want, of course, to determine, in case they are, that they are prime. This is of pivotal importance in modern cryptography, and consequently lies also at the foundation, for example, of e-commerce and other extremely important developments. Now, it turns out that you can do that very, very efficiently by consulting, by employing tosses of a coin. So a prime number is something like 5, 7, 11, and so on. Don't challenge me to give you a further example. Well, 23 is also an example, as is 2 to the 127 minus 1, for those who, who encountered that number. But, so this is a number without divisors. And to say about a number that it is a prime is a special case of a mathematical theorem. Now, it turns out that you can determine that the number is a prime. And you can do it in a way where sometimes you are wrong, but the probability of error is minuscule, not larger than 1 over a million, 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 million. So compare that, danger of error to the danger that lurks, in any one paper, at least that I write. I don't want to insult anybody else here. No, but seriously, so the speaker before me spoke about geometry and proofs in geometry. It turns out that one can also establish theorems in geometry by that method with a little bit of work. And then, for example, you can prove that if the angle bisectors of a triangle are equal, the triangle is isosceles. You can prove that, and you can derive a proof which has a certain very, very small quantifiable probability of error. Now, the next example that I want to cite is speaking about interactive proofs. So maybe you saw yesterday that proofs and mathematics in some sense is a very solitary, reclusive occupation. You sit, you and your pencil and a piece of paper and maybe a few books. Of course, people do interact, but not in the sense that in the precise sense in which this is used in computer science. So it turns out, and I don't have the time to go into details because I asked for 2 hours and I was turned down. So, but it turns out that literally you can prove that you know something. So consider yesterday's play, Kathy. So she had a proof, presumably the hint was of the Fermat conjecture. And she had that proof. Now, she was quite generous and maybe careless with it. But the more prevalent scenario is that people are very jealous, of that, and they are very much afraid. There is a saying that goes, even paranoics have enemies. So you have to be sometimes very careful. So it turns out that within a very carefully quantifiable and very precisely described framework, she, Kathy, could prove, let us say, to the editor of the Transactions of the American Mathematical Society that she possesses a proof, a solution to that problem, a proof for the Fermat theorem without, these are called, consider this fantastic name, zero-knowledge proofs, without revealing anything about the proof, anything at all, provably without revealing anything at all. Now, that is one of the wonderful paradoxes, paradoxical results. It's not a paradox in the philosophical sense. One of these wonderful paradoxical results created by computer science. So whoever wants to know more about it should attend either my lectures at Harvard, and I'm sure that topic is also discussed here at the Courant Institute. This is, by the way, also a technologically extremely important result, because you know how you log into the computer and you identify yourself by a password. Now that is a very bad method, because the password is going over the communication network and can be captured. In fact, my computer at Harvard was broken in 5 times during the last 2 months by capture of a password. But it turns out you can authenticate yourself to the system by a zero-knowledge proof, which has the property that with an overwhelming probability, it is the computer knows. Let's disregard what that means. Another favorite topic for philosophers. But here it's completely quantified. The computer knows it's you who is talking to it. And yet, somebody who observes from the side gains absolutely nothing from that conversation. Now, how much more time do I have?
2 minutes.
2 minutes. Okay, we'll do a lot in 2 minutes. The last topic I want to discuss is another thing which is going to have, or may have, if successful, an enormous impact on mathematics. And that is the question coming under the arcane name P versus NP. So a picture is worth 1,000 words. So I'm going to describe to you a typical problem, which is like a game. Consider that you have a board, a square board divided into small squares like a chessboard, which is, however, untypically, let's say 50,000 by 50,000. You know, computer scientists, so 50,000 by 50,000 has 2,500 million squares. That's typical of computer science. Anything below that doesn't merit consideration. Now you have domino stones. They are square, and they have colors on their edges. And there is a certain variety of domino stones, and you have to fill up that board with those domino squares of those varieties in a way that adjacent squares have the same color. So that's a good fit. If, in case you don't see, it's red with red. Red with blue is not a good fit. So this question, given a board like that, and given those dominoes, is there a solution? Is there a tessellation of that board by these dominoes respecting these constraints? Well, we want to answer, we don't want to try all possible ways, because I'm sure everybody here knows that this would absolutely exhaust, you know, the lifetime of the universe. But for example, is there a computational method, algorithm so-called, in the program that answers that question in, let us say, 1,000,000,000 or 100,000,000,000 computational steps? I don't want to, you know, advertise for Intel, but for the new megahertz processor, that is a computation which is entirely feasible. We don't know. I don't give you all the parameters of that problem because, you know, not everybody is close to it. But now we come to the surprising aspect. If it turns out that there is an efficient algorithm, computational method for that problem, then you would be able to construct automatically, computationally, proofs for very, very complicated theorems. It's not in the domain of those probabilistic randomized proofs I spoke about before. There is that connection. Again, I cannot describe it in full. So now there is going to be the issue whether mathematicians are going to be Luddites and hate these intrusions of computer science into mathematics, or whether in fact these new ideas about proof and what a proof is and what it can achieve and how it can be achieved, whether those ideas coming from computer science are going to be also accepted and influential within mathematics. I have a good guess about that, but that can be opened for discussion. Thank you.
Thank you. Thank you. And I think that's certainly something we can start talking about. Do these work? Can you put those on? I think we'll all sit down. 5 minutes. For 5 minutes, I think we will discuss here. We will have another session, and then maybe if there's some really burning questions in the audience, we'll take just a couple before the break. So I might add to Michael Rubin that there are many seminars that we sit through where the proofs seem to be zero knowledge. That is, nobody knows what anybody's talking about, including the speaker. So I don't think it's such a big deal, but in fact...
Now in typical mathematician's fashion, he claims that they knew it all along.
Yeah. But more seriously, you say, so let me ask a question and then I think I'll just start it off. You say that you have mechanisms to decide if a proof is correct by asking questions or even not even divulging information. So to say we took a proof of something like Fermat's last theorem, which cannot be done in one page as far as we know today, is it realistic? Are these realistic issues? I mean, are these just theoretical constructs, or is this something that if we were really eager, I mean, we could ask Professor Fine whether he believes that Fermat's last theorem has been proven. He believes proofs that are less than one page, clearly. So the question is it realistic to have these theorem checkers, or whatever they are, actually work on something which is a few thousand pages long?
Whom do you want to?
You.
All right. So I would boldly and maybe somewhat rashly say yes. Namely, the proof to begin with has to be completely formalized. Formalized to an extent that makes it in the formalized form incomprehensible to human minds. In the same way that the addition, if you consider an addition of a column of 2 million 10-digit numbers, so you have that addition and at the bottom you have the sum. Now that is computer checkable, but is really not comprehensible. So the first step would be an automated mechanism for turning the proof, maybe interactively with the happy solver of that future problem. One of the problems the Clay Institute has offered $1 million for the solution of. So interactively, but mostly automatically, the proof is being turned into a completely formalized proof. Now that completely formalized proof is going to be easily checkable if you have the correct formalization. What I was talking about is that after that step of formalization, and now seriously, there is a process by which very rapidly the person who's holding that proof can convince somebody else, the doubter, who is asking, by the way, random questions. So he can convince that doubter that actually in this, the prover's hand, there is a proof. Of course, it's going to be within a computer. Now, that's the surprising aspect. But I wouldn't be surprised, computer science took strides that exceeded the imagination and the predicative power of even very serious people and good scientists. I wouldn't be surprised, and this doesn't have to do with AI, I wouldn't be surprised if there will be mechanisms, say, within the coming 10 or 20 years, where this kind of formalization and check would be possible, and for the paranoid, also zero-knowledge proofs.
Okay. On my left, what happened to Jack Schwartz? Is Arthur Jaffe and Professor Tom Nagel, who will be introduced later, but they are going to participate in this discussion. And in fact, do you guys have any comments or questions at this point?
Please. I'll hold off.
Speaking to
I guess I just have a small question for Dusa McDuff. I've always been skeptical of evolutionary explanations of the fantastic rational capacities that allow us to do the kind of mathematics and physics that you described. I know it was kind of an obiter dictum for you to address this question, but why do you think that the adaptive pressures under which our brains or minds were formed would actually result in capacities that would have these consequences?
Well, I don't see, for one thing, I don't see what other mechanisms there are. I think, you say there's the adaptive pressures. Well, there's a pressure, for reproductive success, but there's also a separate sort of evolution of culture. And you can make my life more fun by creating lots of interesting ideas, and you can explore things without immediately affecting your reproductive success, but somehow just affecting the whole culture around you. I mean, it seems to me that Western culture has been very successful, unfortunately, in some senses too successful recently. And I just don't see any other mechanism. I think that our minds develop, our culture develops, our language develops, our mathematics develops, all in relation with the world. So perhaps you can make another suggestion.
Now, I just think the argument, if not P, what else is not in general?
Well, I'm not a philosopher. I was just putting a statement out there. I'm glad you challenged me on it. I'd be happy for other people to contribute.
Well, I'm probably on Tom's side on this question. I don't want you to feel ganged up.
That's okay.
But I mean, if you tell an evolutionary story, I take it that's a story of a very, very specific sort, which involves standard evolutionary mechanisms. And,
talk into the mic.
I'm sorry.
Talk to each other.
Yes, I'm sorry.
Thank you.
Maybe we should pursue a different topic. Yes.
He was a bit intimidated by that. Yeah, Michael. Yeah, speak into the microphone.
Yes, I think your point was really a very interesting one. Yes, I'm now afraid not to speak into the microphone. I think that we have to take into account not only the early stages of evolution, where we were fending for ourselves amongst predators, foraging for food and so on, but of us as social animals. And I think that the social interaction, and especially after the advent of language, which in itself is a mystery, and you would say, well, if you refer to language, you haven't said anything, promoted the development of higher and higher level of abstractions that we share. And there is no doubt, say that if we look at the work presented here, and some of the material I spoke about, it all is an example of very, very high levels of abstraction. And society maybe had a certain selection for the people with ever increasing verbal capabilities, articulation, and also higher level of abstractions. These were the people who understood the organizations, who put together social and other organizations. So it's not just the survival, this is politically very incorrect. It's not just the survival of the fittest, but maybe also the survival of the smartest.
Okay. Dusa raised a question about saying her work cannot be reduced to a calculation and of the type of problem she was talking about, but there are problems that do eventually reduce to a calculation. This is something we see with the proof of the four-color theorem and the proof of the sphere packing problem recently. And I guess with that, maybe I'll ask questions from the audience relative to that, what they think of the role of computer in proof in that sense, or Jack Schwartz, who certainly might want to comment on this. As we take a few minutes from the audience, I think, at this point, and then we'll take a break. Yes, and when we take these questions, if you're back there, they will bring you a microphone, and if you're near the front, you can come up to this microphone up in the front here. Yes, sir.
This is part of the distinction between proof theory and model theory. Like you mentioned Gödel's incompleteness result, but there's also like the Leverheim-Skolem theorem, which said even though you can construct a theory where there are unprovable theorems, in a model, you can have satisfaction. And like you were saying before, the proof theory gives you things like computability. That is, recursive functions will give you an end result that is, it terminates at a given point, and you have a proof. And model theory will give you it doesn't satisfy in the model. That is the distinction between model theory. Logic, since the time of Gödel, has gone these two traditional paths, proof theory and not provable within a theory, but obviously true. And that is they are true, once you move up a higher level, like Jensen's results will not, obviously don't satisfy Gödel's, but they do show that there are true theorems, even though those theorems can be demonstrated within the theory at the level that it holds at. But the model will...
Is everybody back? Great. So we'll continue. Move straight ahead. So the next panelist who will make a small presentation is Professor Arthur Jaffe from Harvard University. He's both in the mathematics and physics department, so he'll bring a new angle on this, the physics side. He's also, is it the head of the Clay Institute? Or he's involved with the Clay Institute, I know that, which is a new institute which sponsors mathematics research and prizes as well. Professor Jaffe.
So I'll say a word before I start speaking that my talk I prepared in advance and it overlaps a little with two of the other panelists, but I think I'll just stick to it because it will provide a different point of view. We prize proof in mathematics. So my remarks relate to each noun in that sentence. Proof. The potential of mathematics is unique in science. Mathematics both reflects the natural world and forms the basis for the physical sciences. It's alive, universal, and perhaps immortal. Extremely simple statements, though, can be elusively hard to establish by proof, with discovery taking years, or we know about Fermat, which took hundreds of years. So mathematics retains an air of mystery. And we heard in David Auburn's play, the question of verifying whether a given mathematical argument is correct can be extremely difficult. And this is true even to the author of the argument herself. The question whether verification is as difficult as discovery is really related to a famous mathematical problem, the one Michael Rabin alluded to, and which I'll come back to later. Mathematical proof transcends verification in other sciences. In physics, chemistry, biology, one goes to the lab, as Dusa pointed out, to check out a hypothesis. Now, a few astronomy experiments or physics experiments can be carried out to multi-decimal point accuracy. There are famous ones with perhaps 10 or 11 decimal points. But that's the exception, not the rule. In most science, verification is qualitative, and if it's quantitative, then modest accuracy is the norm. And the experimental laboratory for mathematics, however, is mathematical proof. So here, one can nail down, with luck, a hypothesis with the certainty of logic. Mathematics also has a theoretical side. One formulates hypotheses, checks special cases, and gains insights in many possible ways, including calculation and computer experiments. More often than not, one's original idea needs modification and refinement, and sometimes even complete revision. Some have to be thrown out before you can frame a hypothesis. This theoretical side of mathematics, I think, is exactly the same as the norm in other branches of theoretical science. However, the natural scientist has the laboratory to rely on and therefore is not driven to the necessity of mathematical proof or to its intrinsic beauty. So mathematics itself is both a science and an art. And I'm happy to see the current increase in popularity of mathematics by the general public, seen by the forum today, and also the appreciation of its artistic side. I talked about this at length in a paper with Frank Quinn 7 years ago, and won't mention it much further, except to say the motivation for that came from the fact that over the last 20 years, the subjects of theoretical physics and mathematics have probably had as much interaction as in any other period of development. The physicist Eugene Wigner gave a famous lecture here at NYU in 1969, perhaps here, speaking about the unreasonable effectiveness of mathematics in the natural sciences. Today, I think one could speak just as much about the opposite. That is, the unreasonable effectiveness of physics in mathematics, and we heard some of that from Joseph McDuff. However, because the training in theoretical physics and mathematics tends to be extremely different with different sociologies and points of view in the two communities, there's some clash of these two cultures when they interact. And this has not yet fully played out. There's, for instance, words that the two sets of people use that have completely opposite meanings, like formal, and ones that have different meaning, like proof. But we don't have time to settle that question today. Mathematics, that's the second noun. Mathematicians are problem solvers and dreamers. The former activity focuses on solving specific questions, the latter on developing and understanding vast structures of ideas with interrelations between them. Some mathematicians identify more with one activity or the other. Some mathematicians go from one mode to the other. And I see in the audience all three of these. The formulation of problems serves to focus on important questions in particular areas, but one can never tell where it leads. And one famous mathematical problem, which is closely related to the question about whether it's harder to check a proof or to discover it, has recently been shown to be related not to the domino game that was talked about by Michael Raymond, but also to another very popular game, Minesweeper, which everybody who owns a Windows PC has probably heard about, or their kids have shown them or played. So I wanted to show a slide. So there's a mathematician Richard Kay in Birmingham, who recently showed that this Minesweeper game the Minesweeper game, you have a board, and this is a large one, in which the squares are marked. The numbers correspond to the number of mines touching the square that's numbered. And there's some mines that are marked, like the one here. And the idea of the game is to uncover all the squares that don't have mines. And Richard Kay showed that you could use Minesweeper to build a computer. Namely, you have a Minesweeper wire. There's a configuration of Minesweeper. So this is mathematics. So I would say this is mathematics. It's hard to, I can't see this. Okay, I want to look at the top. We have this Minesweeper wire. And by having the configurations where x denotes either a mine or not a mine, and x prime the opposite, if there's a mine at x, there's no mine at x prime, it propagates the signal, this configuration propagates the signal from left to right and acts as an electrical circuit. And a NOT gate is the simplest logical gate, is this configuration here, which switches the mine to not a mine, or the not mine to a mine. And by a more complicated construction, it's illustrated here, but I won't go into it, you can do the other thing that's used in the computer, an AND gate. A NOT gate turns a variable that's on off, or a variable that's off on, and is used as a computer memory element. An AND gate takes two inputs and creates the Boolean AND of the two, and is the other basic element in building a computer. Well, once you have a correspondence between Minesweeper and a computer, you also relate it to this famous P versus NP problem, which is one of the most difficult and challenging and important mathematical problems of the era. The question is whether an arbitrary configuration can be found in polynomial time to be a allowed configuration in Minesweeper. If you want to read more about this, look in the October current issue of the Scientific American, where there's an article by Ian Stewart. So the third noun, prizes. Scientific prizes have been with us for a long time. In her book, Longitude, Davis Sobel describes the prize established by the British Parliament in 1714 to determine longitude to within half a degree. The monetary award of £20,000 then would be roughly $2.5 million today, larger than any prize I know of for science. The Nobel Prize is more recent, but it's assumed a place in popular culture that far transcends the monetary value attached to the award. This focuses attention on science and scientists. It's my belief that science prizes are very relevant to society, but much less relevant to the course of science. Prizes focus tremendous attention. They influence the way society thinks about science. They contribute to the value that society places in science. But for scientists, I believe that the intrinsic glory of discovery, the joy, the possible immortality that can follow from a milestone discovery far outweighs the more mundane question of wealth. So the Clay Mathematics Institute is a private nonprofit foundation whose sole goal is to increase and disseminate mathematical knowledge. And on May 24th, we announced a $7 million prize for the solution of 7 classic mathematics problems with $1 million assigned to each. But we certainly worried about whether the prize would make mathematicians work more secretly, guarding their ideas, which was another theme in the play Proof. In order to address this issue and to encourage all publication of partial results, the CMI, or Clay Institute, rules specify a committee of experts will take into account the influence of prior work in recommendation of any prize. Well, the reaction to the prize announcement was overwhelming. One gauge of the public reaction is the fact that within a week of the announcement, over 1 million persons visited our website, making it completely inaccessible for several days. Over 1,000 persons have sent in proposed solutions to a problem, even though the rules especially disallow it. There's an editorial in Nature magazine that I was going to quote, but I seem not to have time to, saying that basically it's good to celebrate the intrinsic value of challenges, and they bring forth the eternal fascination that mathematics holds for a number of mathematicians and for the rest of us. I've brought a 3-minute video made by ABC News about this announcement and the P versus NP problem in particular, and you can watch it during the break. It was shown June 2nd on Good Morning America. Let me summarize by saying I'm comfortable that mathematical proof, unlike us, is immortal. Thank you.
Well, thank you very much. I know someone who is working on these problems and has only solved 3 out of the 7, and until he gets more than half marks, won't hand in his paper. They are hard problems. They're carefully chosen. Your money seems safe for the time being. Okay, our next panelist is Professor Tom Nagel from the Philosophy Department at NYU. He also had connection with Princeton, used to be at Princeton in 1980, I understand, to convince you that he's obviously had a great impact there. I still thought he was there recently because they talk about him there all the time. Professor Nagel.
Proof is a method of arriving at knowledge, and I want to talk about the relation of proof and a priori reasoning, of which it's a particularly rigorous kind, to human knowledge in general. Obviously, proof, mathematical proof, proof that something follows logically from a theory and so on, these procedures provide an example of a method of arriving at human knowledge and perhaps a model for aspiration on the part of types of understanding in which such rigorous methods as exist in mathematics are not available. I think that the aspiration is understandable, though the model can do a good deal of harm if an attempt is made to apply it to a field where it's not appropriate. I once heard, I think it was the anthropologist Marshall Solins, use the wonderful expression epistemological hypochondria to describe the problem of the situation of fields of knowledge such as the social sciences when they look at the example of mathematics and the physical sciences. Reasoning in logic and mathematics has two characteristics which mark it out. A high degree of at least possible certainty, and I would say an unquestionable objectivity. I won't say much about certainty, which depends on the existence, even in the case of the most complicated examples of mathematical reasoning, of breaking it down, at least in principle, into a series of simple and self-evident steps. Even though mathematics, as it's actually conducted, uses many tools, which are the product of all of these steps having been taken historically in the past, still they are there in the background. And in principle, at least, a mathematical or logical proof is one which depends on steps so clear and begins from starting points so self-evident that anyone who understands them is simply bound to accept them. By objectivity, I mean that the conclusion would be true even if it hadn't been discovered. Objective truths are mind-independent truths. Proving a theorem is not like writing a novel or a play, even though both require some form of creativity. It is the arrival by methods of reasoning at a conclusion that one then sees to be true and cannot help believing would have been true and was true before it was discovered, and would have been true even if it had never been discovered. Now, I realize this is controversial. I suspect that it is the outlook of most practicing mathematicians, but I know that the alternative view that mathematics is created in a sense that is incompatible with its being objective in the sense that I've described, is also one that is held by some people. But I think that if you actually think about any mathematical conclusion that you yourself might come to, even a simple solution to an arithmetical question, it's very hard to think that this is something that you are bringing into existence rather than something that you are seeing to be true. For this reason, mathematical knowledge is philosophically very mysterious. We generate it entirely out of our own minds, and yet it gives us, I think, the strongest sense of contact with an objective reality whose existence and character is independent of our minds. It is precisely in thought of this kind, in detecting logical consequence and the relations between numbers, that it is impossible for us to think, this is just how things seem to me. This is how it is from my perspective. As we can think about the fact that the sun is rising. We are capable of transcending the appearances in a case like that, because we can place our impression that the sun is rising in the context of a more objective picture of what is really going on, namely that we are standing still on the surface of the earth, and the earth is rotating, and therefore we get the appearance that the sun is rising. But for a priori reasoning about logic and mathematics, we can't step back from the way things seem to us self-evidently in that way. We come to a ground level beneath which it is impossible to penetrate. And for this reason, a priori reasoning has a fundamental place in the idea of objective reality. It sets a limit to the subjectivity that we can ascribe to aspects of the way the world seems to us. Once you start on the path, which is the path to scientific knowledge, of recognizing your own creaturely contingency, and recognizing that a great deal of the way the world appears to you is the result of an interaction between yourself, your sensory apparatus, all kinds of contingent things about your human makeup, and an external world, you have to recognize that a lot of the initial appearances are going to be not fully accurate, misleading, imbued with your own perspective. But to identify something as subjective in this way, to identify the appearances as mere appearances, you have to place yourself in a more objective picture. If you're going to say, for example, as many people have said, that colors are just effects on the human perceptual system and not really properties of external objects, you have to replace that perspective with a physical theory of the reflectancies of surfaces, plus some theory of the effects on the retina of the reflected light, and so on. And in order to do that, you've got to be able to construct theories that will explain the appearances. Now, apart from logic and mathematics, these extremely abstract subjects, reasoning is what permits us to formulate the physical and other scientific theories as possible pictures of an objective reality that permit us to explain the appearances and substitute an objective conception of the world from the initial perceptual one. Fortunately, the world is law-governed and mathematically describable, and this enables us to transcend the subjective experiences with the help of a priori reasoning that allows us to construct theories, deduce their observable consequences, and confirm or disconfirm them. That is how we have made the trip from arithmetic, geometry, the measurement of space and time, to Newton, Maxwell, Einstein, string theory, and beyond. Nothing comparable is available in the other areas of human knowledge and inquiry. But I don't think that that's a reason for giving up on objectivity in those areas. There are really two ways of giving up. One is subjectivism, to say it can't be made rigorous in the way that math and physics are. Therefore, everything else is just a matter of perspective or appearances, how it seems to us. Take the theory of value, for example. The other is scientism, to try to find an interpretation of those other areas which reduces them to something that is mathematically and scientifically and physically describable. I think that the problem of the status of objectivity in human knowledge is really the question, how much objective truth can we hope for without anything like the standards of proof that are available in mathematics, where objectivity is simply undeniable. I would myself favor continuing to look and looking for methods that are appropriate to the subject in question.
Thank you very much. So our final panelist is Professor Jack Schwartz from NYU, the Courant Institute. He is a mathematician, a computer scientist. He's worked in many, many different areas. It'll be very interesting to hear his view on the subject. Professor Schwartz.
When they contemplate the celebrity of rock stars and the groupies who pursue them, mathematicians and scientists, even physicists sitting on top of billion-dollar budgets, have a way of feeling neglected, and perhaps this event reflects some of that disappointment. I'm a little reminded of a conversation I had with a group of code breakers at the National Security Agency who, over beers, were complaining that the general public did not appreciate their work. To which I could only respond, but your work is supposed to be super secret. Having said that, I want to sneak up on the question that is the title of our panel: what is a proof work? What is a proof worth? Now, I'd like to say the following. The activity of mathematics involves an interesting playoff between intuition and formalism. Okay. The formalism has several interesting properties. It's a stable formalism that has stabilized over the course of a few centuries of work, and has become stable enough that it's computer checkable. Okay, so it's a language that is as guaranteed as any formal process can be by computer checking. As far as we know, it's consistent. That's all one can say, because we know we can't prove its consistency. But as far as we know, it's consistent, and I think that its consistency, the consistency of this language which we are able to speak, creates the illusion of truth. Okay, because we speak it, we find no formal obstacle to continuing to speak it, and having done this for long enough, we believe ourselves to be speaking some kind of truth. Okay. On the side of intuition, the intuitions are drawn from a variety of areas, principally from counting and arithmetic, from geometry, our experience of space, and from the more primitive experience we have with assemblages and collections, with the elementary properties of sets. Okay, and since the human mind is really not very good at dealing with pure formalisms, and one rapidly loses one's way in any purely formal structure, we can only progress into these formal structures by finding intuitions which will sustain our arguments. I think that's what Newsom McDuff was saying in different terms. Okay. The fact that mathematics is fully formalizable and has a stable computer checkable formalism or language as part of it means that arguments in mathematics can be very long, and that people will take a 10-page or a 100-page or a 1,000-page argument seriously in a way that they wouldn't in other fields. Okay. In physics, the situation is quite different. Okay, the attractiveness of an argument in physics really comes basically from its primitivity, and it's much more important to find the simple, direct, and primitive argument than the kind of elaborate argument that the mathematician is happy with. It's like the difference, I think, between a Faberge egg, which one can admire as a work of art and for its elaborateness, and a sledgehammer, which doesn't want to be elaborate and which one admires for its utility and effective primitivity. Okay, so the physicist will use mathematics, as any scientist will, where one can make some sort of effective contact with mathematics, but knows enough not to take it all that seriously, for the simple reason that mathematics assumes its axioms to be true, and the physicist always knows that his axioms are not true, but merely approximations to some unknown truth. So the situation is quite different. One sees that one sees that, say, in the situation in quantum mechanics, okay, where I think it's fair to say that after 80 years of fairly intense intellectual effort, there is still not a consistent intellectual structure there. You know, the people have worried about inconsistencies on and off since 1920. Nobody has been able to patch that up into a consistent whole. But in the last analysis, nobody cares, because there's another basis for judgment, which is experimentation. So that even though the intellectual structure may eventuate, you know, which has a lot in it. I don't mean to downgrade it, but at the bottom there's some piece of nonsense that nobody has been able to resolve. That's not fatal as it would be in mathematics, because it all conforms to experiment, which is more important. So in that sense, I'd like to end with a pessimistic remark. Mathematics is a language in our heads, okay, and proof is an aspect of that language. There's no reason why the world has to correspond to any language that we have in our heads, because in the last analysis we are, you know, we're cousins of the earthworm, and so we have to regard our own thoughts, as physicists do, with a certain caution. So thank you.
Switch is on. Thank you. Okay, thank you very much, Jack. So now, actually we were given a few extra minutes, so I think we have about 15 minutes of discussion time, of which we'll start with half of it amongst the panel, and the second half, again, the general public. So let me start by asking the right half, the earlier speakers, if they have any comments about the three speakers who spoke in the second half. Yes.
So I, of course, enjoyed all the presentations. They were extremely instructive. I want to direct some comments at Tom Nagel's presentation. And the problem that he raises is, in fact, an age-old one. It goes back to the issue whether the Platonic point of view that ideas such as numbers have an independent existence, and all that we do in mathematics is uncover their properties. Now, that is a very useful hypothesis, working hypothesis for the working mathematician. There are all of these gems buried there about properties of numbers, for example, and we are just uncovering them. They are there. But there is a certain limitation to that. While we are in the realm of natural, so-called the natural numbers, which are our old friends, 1, 2, 3, etc., mathematicians since, well, the last century is not what it used to be. So not the last century, but the one before that, the 19th century, are also considering, and there is an extensive activity considering infinite numbers. Those who know that, those in the know that this is a very interesting and important topic. Now, when it comes to the existence of various infinite numbers and their properties, and you can calculate with those numbers and do many things with them which are very similar, others which are very different from the properties of natural numbers. When it comes to those properties, Platonism clearly breaks down, and people can make divergent assumptions about properties, existence or non-existence of certain types of those infinite numbers, and those assumptions have an implication, so to speak, down here, even on the properties of natural, or provability of properties of natural numbers. It is related to a question that we had here about Gensen and completeness and models and so on. Now I want to make one other comment relating this objectivity and finality of proofs in mathematics. I think that there is a need to cope with the introduction of randomized methods into proving theorems. So one can use randomization to show that a certain natural number is a prime, and that has very, very important implications in practice, because, for example, the safety of bank accounts at Citibank will depend on that. If there is an error there, then that would be pretty bad. And this is established, as I said, by use of randomization. So what kind of a proof is it? The New York Times, when this method was suggested 25 years ago, I was surprised to see a lead article on that, editorial on that, in the editorial column, saying a revolution in mathematics, the end of certainty in mathematics. So but the editor of the editorial page at the time had scientific inclinations. So he put the finger on that. And we still need to cope with the significance of that innovation, significance in philosophical terms.
Thank you. Tom, you want to respond?
About the first question, Platonism, it is, of course, a matter of profound disagreement. But I guess my only question about the transfinite numbers case is whether the examples in which alternative properties can be ascribed to them can't be interpreted as just the discovery of more variety, more complexity, rather than the discovery that there is no objective truth about these matters. The second point, the fact that there are now possibilities of proof, so to speak, that is not certain, with a minuscule possibility of error, is, I find, in a way, particularly interesting because it shows the possibility of separating the idea of certainty from the idea of objectivity, even in mathematics. Because there is no question, even in the case where the proof does not give an absolutely certain result, that the result is objectively either true or, with a very, very small probability, false. So I think that one can have objectivity without truth. And the question about mathematics and about other fields is, how far can you allow those two ideals to separate before objectivity begins to disappear?
Thanks. Kit.
Can I make a remark about Platonism? I don't think that, given what we know about the theory of transfinite numbers, that it's clear that Platonism breaks down. What it means that Platonism is more problematic because there are huge gaps in our knowledge, and it's very unclear how they're going to be filled. So the issue is just how many points are there on the line, and very simple hypotheses about how many there are can't be settled within current mathematics. So it's rash to come to the conclusion that there's no objective fact of the matter as to how many there are. And indeed, Gödel, who was one of the people who helped prove results of this sort, thought there was an objective fact of the matter. And interestingly, for our present discussion, he thought that certain non-deductive methods of reasoning might be employed actually to settle this question. So I think it's rash to say that Platonism clearly breaks down in the realm of the transfinite.
Yeah, thank you.
Could I just show?
Yes, sure.
So this is really, I wouldn't, characterize myself as being rash, but it seems to be a very open issue. So the question he was referring to, there is a notion of a set. So for example, one can talk about all the people in the United States, that is a set, and there is a notion of a subset. For example, all the people who are exactly 25 years old now, or all the people with, say, red hair, or for that matter, with any hair on that. So these are subsets. So we have a feeling that we can look at a set, say, of 7 objects and form all the subsets. it's easier to look at the set of 3 objects. There are 8 subsets. And the corresponding question that was alluded to, how many points there are on the line, in a line segment, is really the question, how many subsets does the set of all integers have? And this is a wonderful opportunity for a person who can't make up their mind. Because it turns out that there are a number of consistent answers to that. And I would say that we have to suspend judgment until somebody gives a really generally accepted answer. Platonism maybe is not dead, but has a very high fever.
Well, thank you. Perhaps we could steer that a little bit towards maybe Jaffe's comments in, do you think any of the problems you put forth might fall into this horrible position of, I don't know about undecidable, but that they may not be solvable, so to speak?
Well, I think somebody described these prizes as the most cost-effective advertising ever because they didn't expect that problems would be solved in our lifetimes or maybe the next generation. I'm not sure about that. I think that a number of problems that we put forward are very difficult.
I mean, the problems you put forward are sort of mainstream problems that a lot of mathematics depends on their truth, so they, not that the continuum hypothesis it's a very good problem, but the problems are very mainstream and have great impact on many, many fields, just to clarify that. Yeah. So, yeah, you were saying, sorry.
Well, I know that a couple of these problems are so difficult, and one in particular I'm thinking about that I couldn't imagine how one would even start to think about answering the question. Whether it's undecidable in the logical sense, I doubt, but whether it could be proved as a mathematical theorem is a different question.
Let me change it, but in the play, I think one thing, the play is called Proof, and we saw a lot of conjecturing in the play, guessing what's the truth, and I feel that throughout this discussion, conjecture, Dusa did bring it up, that physicists are able to make fantastic conjectures, but mathematicians are also very good at conjecturing, and these problems that are being discussed for prizes and so on are, I think, some of them the greatest conjectures ever made. I feel that, and physicists, as was pointed out, physicists like to explain how simple what they are doing is, and mathematicians try to explain how complicated what they're doing is. And this is not right, because mathematicians do think in similar terms. They do also have to have intuitions to arrive at the answer and make conjectures. So I'm a bit disappointed that there aren't prizes for conjectures, because I think there are 2 parts to mathematics, as Paul Erdos, a famous mathematician who died a few years ago, he said there's proof and there's conjecture. He was fantastic at conjecturing. And I think that we are, underplaying the discovery and conjectural side, which I think is as important in the end as the proof. You have to know what's true before you can prove it in all domains of life. So, all right, I'm not supposed to talk, but that was...
Could I say something? Yeah. So I believe also that the conjecture is the most important and exciting part of mathematics. I think that formulating new questions is what mathematicians love to do. But the reason we decided to have prizes for classic old problems is because we knew these problems are hard. All of these problems have been worked on for 30, 40 years, some of them for well over 120 years, 150 years. And we know that good people have unsuccessfully worked on them, so they are difficult problems. At the frontiers of mathematics, things move very quickly. And it's very hard to say which are the most important questions, and so we just steered clear of that.
Okay, unless the panel has something quickly to say, I'll open it up to the floor. Okay, are there anybody who have Any comments or questions? Yes, you were first.
I'd like, if I may, to bring to bear on the play some of what we heard this afternoon. And to do that, I'll invoke a distinction made by the distinguished French mathematician Dieudonné, who says that a mathematician is someone who has published the proof of at least one non-trivial theorem. Now, by that criterion, I'm sure there are people in this room who qualify as mathematicians and some who don't. And what I'm curious about is, in the play, we saw someone who was she or was she not a mathematician? She had written a proof of a non-trivial theorem, but had not published it and might not even be interested in publishing it. And I found that many of the emotions that were depicted in the play had to do with that unusual situation. And I'm sure I'm not the only person in the room who's curious as to whether the distinguished mathematicians who have published more than one proof of more than one non-trivial theorem have ever had an experience or resonated to that experience, whether in your own personal experience you've ever been in a situation or known someone who had the proof of a theorem but didn't or couldn't publish it.
Thank you very much. So that's a great question. Any answers here?
Well, in fact, Gödel refused to publish his proof, I guess, of the independence of the continuum hypothesis.
Is this a fact, or is this debated? Paul Cohen.
I was told
okay.
this, and then Paul Cohen.
I've heard different views on this.
Oh, I see.
But that would be a good example, of course.
Well, I'd like to say sometimes there are examples where a senior mathematician proved something, but a junior mathematician's also proved it, and then certainly the senior mathematician often backs off and lets the junior mathematician publish it. So, I mean, that's a sort of sociological question, right? That's slightly different.
Sure.
So this touches upon the question, which is very interesting sociologically, whether a person on a desert island, even assuming that he or she are great mathematicians, whether they would continue working in complete isolation. It's somewhat doubtful, but there are examples for not only in mathematics. So I've heard, I didn't know the person, there was an extremely important physical chemist of the theoretical variety, Onsager, at Yale. And it was being said about him that he had earth-shaking results that he worked out and that he kept in a drawer. Maybe the person was so sure of himself and had already that much recognition that, well, some of those things he let go. But it is unusual.
My own answer to that question would be that she's definitely a mathematician, and I don't think Dieudonné was right. I mean, what's it got to do with publishing? If you prove a theorem, you prove the theorem. That's a separate issue, but that's my personal view. Let's take another question from the audience. Yes, sir. Could you? Yeah.
I would like to express just a slight disappointment about the fact that something that's been bothering me for a long time hasn't been discussed here, which I hope would be discussed. And that isn't the unreasonable success of mathematics and physics, but rather the unreasonable success of implication in all of this thing. Implication, after all, is just an artifact of the mind. And it's amazing to me that people have paid a lot of attention to it, and that the only proof, really, that implication has some validity actually comes from physics, not from mathematics. The mathematicians have, I forget the word, they've stolen this idea and made a game out of it. Otherwise, what right is there to expect that P implies Q means not P or Q? The only reason we have to expect it is because it's worked when we attacked problems of this world.
Thank you. Would any Anybody like to comment?
Well, I would say that mathematics is the development of a language. That's one of the things that Jakob Schwarz was saying. So I don't think mathematics is just a game. I think mathematics is developing a language in which you could express a lot of things.
I'm not deriding mathematics. What I want
Could you come back? Excuse me, could you come back?
is what the important, how this artifact of the brain has affected the world. Then the whole idea of implication.
Well, this was part of what I said in my last sentence, in fact. I said, you know, that mathematicians and physicists think about the world in slightly different ways, but why do they talk about the same thing? It's because our minds have developed in relationship with and interaction with the world, so that what we do is valid. I think that you also said that. Yeah. That's the only explanation I can see, that you know, the way we think is not just, doesn't come out of nowhere. It comes out of the fact that we're living beings coming from earthworms, but, you know, earthworms have developed some.
Okay. Okay, these are tough questions. Let's go to the next. Yes, at the back there.
Thank you. There was a lot of talk about objective truth in proof, but if we look at the famous problems at the start of the last century, or maybe it was 1900, the Paris problems, and then we see the most particular example, Hilbert's 10th problem, where the proof concept, when it was finally done, was something that was totally unforeseen by Hilbert himself in 1900. And I wonder if the panel thinks this is possible, that the proof concepts we're talking about in 2000, that there will be something completely different in 2070.
Okay, what does the panel think?
Concepts. I want true. But I was actually thinking that it was open to the notions of truth and proof, either to question either that the informal notion of proof corresponded to provability within a formal system, or even to question whether there was this, whether on the other side we were operating with a coherent notion of truth. So he might have doubts about the standard model being able to do the work that's required, or being able to grasp this informal notion of truth, in accordance with which we could actually see that the Gödelian sentence was true. So you're quite right, if I understood you. These considerations, I mean, I was giving a mere sketch, but these are kinds of philosophical considerations that one would have to raise in considering the philosophical significance of this result.
Thanks. Bob Osserman there? Fellow Bob Osserman, you can...
Thanks. I was really interested in this comment of Kit Fine about a critical point in distinguishing deductive reasoning as philosophers use them, and in mathematics, that mathematicians tend to have constructions. They invent new objects in the course of a proof. And I had a question and a comment. One is, when you ask, could computers do the same thing? Is it a computation? It seems to me it's a different kind of a process than a computational one to think of some construction that's going to work. And I was also going to mention there's a new book by Enrico Giusti, which is only out in Italian so far, but may get translated, where he looks into the nature of mathematics. And this is one of his key points, which has to do with, you know, the old question, is mathematics invented or discovered? And he points out that this is the key process, that in trying to prove something, mathematicians make constructions, and then it goes through a number of steps and becomes a new object that then becomes a subject of study.
Thanks. Yeah, I think anybody who works on Euclidean geometry, writers in their youth, the problems which involve construction are always that much more satisfying and more difficult. So, any comments from the panel? Yeah, we are, as I was warned, running out of time. So I think we should take a 4-minute stretching break, and then I'm going to limit the second half, unfortunately, speakers to 10 minutes each, so we can have a longer discussion period. Thank you.
No,
You have to say.
I can argue that Cantor's notion of a set, which was mentioned, at least as he used it, was a new concept, which allowed actually the formulation of new mathematical results and new proofs. I myself think there probably will be new mathematical concepts that will be discovered. Indeed, my own view is we don't even properly understand the notion of set, and that in order to properly understand that notion, we'll need actually to avail ourselves of some other notions. Of course, I can't tell you what these other notions are, otherwise I would have come up with them. But my expectation is that we will come up with new mathematical concepts, which will help actually in tackling, not only formulating new mathematical problems, but actually solving the mathematical problems that we have.
Could I just
Okay, yeah,
say,
2 more answers and then we'll stop. So, short.
All right. So actually, there is another extremely important example of a new concept, which is actually related to your question. And that's Alan Turing's and Alonzo Church's concept of computability and the negation non-computability. And this is how that question, Hilbert's 10th problem, was resolved in a way that Hilbert maybe couldn't expect. And the notion of computability in Alan Turing's work is really at the...
Perhaps remind us what Hilbert's 10th problem is.
Oh, now I'm on exam. Okay, I'll try. So you can consider equations for integers. In fact, like the equations that were involved in Fermat's conjecture. So an equation like that is x squared plus y squared is equal to z squared, which has a solution, for example, 3, 4, and 5. 3 squared is 9, 4 squared is 16. The sum, even in this august form, is 25, which is 5 squared. So Hilbert's 10th problem was the following. You are considering all sorts of equations like this where you ask whether there are solutions in integers. And you want to have what we now call a computational method, and we now understand, thanks to Alan Turing, you want to know whether it's a computational method which, given an equation and being asked, does it or doesn't it have a solution in integers? The answer comes out, so to speak, automatically. And that was settled very brilliantly in the negative. And Martin Davis, who used to be a faculty member here at the Courant, made a very decisive contribution on the way to that solution. And also a great woman mathematician, Julia Robinson, who unfortunately is not with us anymore. So Alan Turing's notion of computability opened up a new field. And if one looks also at computer technology, that to me is a shining example of the power of the mind. That very theoretical paper written in 1935 by this really suffering person, there was a play about him as well, that was really the foundation for modern computer technology. So yes, I'm very optimistic. There are going to be other great concepts, some of which are going to have very far-reaching everyday life implications.
Thank you. So 1 minute response by Tom Nagel will end the session.
I just wanted to say that mathematics is not unique in this respect. Human progress depends on the constant creation of new concepts which make it possible to address formerly somewhat inchoate questions more precisely. And physics has advanced this way, and perhaps other subjects may make it to greater rigor. I forget who said that every human subject begins as poetry and ends as mathematics. That's my hope.
Okay, well that ends the session, and thanks to the panel.